So hello everyone, my name is Nguyen Huu Noi, and today I will present you the presentation about the feature representation of Auto Encoder for unsupervised IoT malware detection. In this presentation, we will show you the following contents: problem definition, approaches, background, assumed by classification algorithm, a hybrid IA, and some experiments, result and discussion, conclusion and future improvements. So problem definition is follow. So as we know, Internet of Things today is more complicated than a computer network, and the data produced by IoT device is huge and heterogeneous, and the dataset is multi-label or multi-class and is difficult than before to inspect, and we have different attack techniques are used, Mirai and Gatkeep, and we have different deployment techniques on server, on edge, on device, and we need to real time to detect attack. And when we deploy on server, on edge, or on device, so we have the different compute and storage resources, and they are usually limited. So which solution is the most suited? The approaches is follow. The first one is supervised learning approaches. So the supervised learning based approaches is the most of classification problem are called single labels, and in this approach, normal or binary data is used for training. The second approach is unsupervised learning based approach, and in this approach both normal and abnormal data are used for training. And in this approach we deal with multi-label data is a data set. Our method is follow. We use the Auto Encoder for latent representation to find and extract useful features, and use cell-oriented maps to categorize and classify normal and abnormal, which is based on competitive learning method. So first one, we go to the background. The first is the Auto Encoder. The Auto Encoder is feed-forward neural network, and it consists of two parts: encoder, decoder, and connecting by its bottleneck layer. And the mathematical formulas are as follows: z equal fx and equal ia multiplied by ws plus b, and x hat equal jz and equal jfs and equal ad w apostrophe fx and plus b apostrophe, where a and are activation function of the autoencoder, and D is activation of the decoder. It has a rejection, and from this we have the loss construction is calculated as follow: Lx and it has equals square of x and minus by x hat. So second one, you go to principal component analysis, PCA. And as we know, PCA is an important technique for dimensional reduction, and PCA takes the input data points x in RD, where D is the number of dimension, and created a new data point z in RK, with K is less than D. So, and we have some modern PCA algorithm like custom PCA, space PCA, nonlinear PCA, and robust PCA. So the next one, we go to SOM. So what is this? The SOM is abbreviation of the cell organism maps, or its coordinate maps. This maps are cell organism neural networks which can map similar instance to a group in a map, and each neuron is placed next to each other. And it was introduced first time by Professor Cohonen in 1980s. And this map converts a relationship between high-dimensional data items into simple geometric relationship on a low-dimensional display, and it can compress information while preserving the most important topological and magic relationship of the primary data items. Data visualization, feature extraction, and pattern classification, adaptive control, or robots can use SOM to inspect the data, and this method is based on competitive learning. So next we go to the algorithm to chaining some. The algorithm is shown on the picture, and you can see in algorithm 1. So we on the chaining sum, the winning neuron is achieved using algorithm distance, and you can see the formula as shown in the formula 1. The second one, the next neighborhood of winning neuron is finding using Gaussian function as shown in the formula 2. And the next one, the weight update process, is shown in the formula 3. And the weight vector at iteration t plus 1 is updated by formula 4, where dz is a distance and xe is the input, wge is weight, rce is a Gaussian function, delta ge is a trend of the weight update process, and wgt1 plus 1 is a weight vector at iteration t plus 1. Yeah, you can see in the algorithm 1 we have a is the number of approach, we have x is the input, and output is w is a matrix, and we have the main loop, and we have the main loop as shown in algorithm 1. So next one we go to classification algorithm based on sum. So we have given xe, and we need to classify it into appropriate class, and to solve this we make all classes are represented by binary vector ve. The z position in this vector is corresponding to the z class z. If the instance xe is a member of class z, then veg has value 1 and 0, vice versa. The prototype vector is obtained averaging the class vector of training instance mapped to neuron and noted v bar. And the formulation prototype vector is as follows: v by ng is equal sng and divided by sn. And to map instance n to class z, the v by ng is compared to threshold. Threshold can be set to 0.5. And we need to explain about the formula of v by ng is equal sng and divided by sn. Sn is all item which mapped to the n in the neural network, and sng is all item have class z and mapped to the item n in the neural network. With algorithm as follow is shown in algorithm 2. So we have the string is input and the sum w sum, and we have the output p. P is threshold. The algorithm as follow. The first one, the winning neuron is selected from the neural grid omega. The second one, get training instances mapped to winning neuron. The first one, calculate a prototype vector. The next one is compare the prototype vector to threshold, and we had get appropriate class. Yeah. The next one we go to hybrid of IS and SOM. You can see in the picture. So we have two phases of the architecture. The first phase is a feature space of an IA. Yeah. So this phase is used to learn the feature representation of the input data. So from this phase we can receive the code. And the next one is a SOM phase. So the SOM phase can categorize and classify the input to appropriate class, and input of the SOM is the output of the IA phase. So go to experiment. First one, we use the data set n by odd, and the data set contains 9 devices. We can categorize into 4 groups: doorbell, thermostat, monitor, and camera webcam. The more detail about data you can see on the table 1. And to make the experiment we design different chain and test scenario and show in table 2. And you can see in table 2 we have two main groups, 1 and 2. The first group we test on the device D1 and D3 is the thermostat, and the second group is based on camera. So in this group we can make change on one device, and we have make a test on other device. So we have in the first column we test on the same device but different attacks. it and is called unknown attack. And the seventh phase, we have tests on the different devices and different attack on the same attack. So in to evaluate the effectiveness of algorithm, we use accuracy and IoT to explore the effectiveness of the algorithm. And in this paper, we only report the AUC because if we have the accuracy, so result is very long. And we have divided the training data into different ratio from 1% to 5. So it's the ratio that is ratio data between the benign and the attack data. And we also perform attack test on attack detection, unknown attack detection, and attack detection on the other. So next one, we go to unknown on new IoT attack. In this slide, you can see the result when we make the test on the one device, but we change on one type of attack and test on other ones. So in this one, it seems that the experiment so that the result so that the ISOM is something better when the data is not balanced, and on the case when data is balanced, the PC sum is something better. But when we summarize it on the graph, you can see that the ISOM in the green is blue color. It we can see that it's maybe in some case it's more concentrated than the PC or SOM. The next one, we go to transfer learning. As we know, in this slide we aim to show that we can we evaluate the ability of transfer model to different IoT device. The model is trained on a device with IoT attack group can be used to detect IoT on other device. We examine two groups, D1 and D3. Is the doorbell device, and the second one camera is the D5, D6, and D8. The detailed result are presented as following table. As the table 5 is the result of the train and test on device 1 and device 3. So as we can see that we is most we have the ASOM is the result something is better than PC SOM. But the PC SOM is more concentrated than ASOM. The next table 6 is show the result on testing on device 3 and device 1. And remember that we don't have Mirai on device 3, so we have only train on device 3 and test on device 1 GetGip and device 1 Mirai. The table 7 is show the transfer learning. So we can see that we make a train and test on device 5 and test on device 6 and device 8. And so first group of column we make train on device GetGip and test on other device. On second we train on device on Mirai and test on other device. And the table 8 is from device 6 and device 5 and 8. So we might go to conclusion and future improvement. In this work, we propose unsupervised algorithm based on some of our attack detection. We examine intensively and extensively the future representation of AIS in a super approach. The SOM-based classifier is able to detect attack unknown attack in the same device and can transfer to other device. ISOM is highly recommended to use in unbalanced data, while PC SOM is more preferred in inverse case. And in the future improvement, we can apply the representation techniques to latent speed to improve the accuracy. For example, denoising IA, variation IA, and we can test with different size of code or bottleneck, and we combine clustering-based methods with current latent representation to improve the effectiveness of the system. So, last one, thank you for your attention.